Okay, right. So we'll start the session. So here there are a few sections that I need to cover. So since this is the last physics session, I need to cover the moment and the momentum and the turning effect as well. So I will be conducting those two sessions as well. So these sessions are uploaded in the on the YouTube channel, so you can leisurely refer them, right? So here astrophysics and cosmology. So this is the last unit in our syllabus. So when it comes to the astrophysics, we are discussing about the stellar movement and all the related stuff. But here, remember, we have only two equations to deal with here, right? And most of the time, there will be small questions from these sections. So I just want to pay more attention to those calculation types, right? So I have uploaded this tutorial, this presentation in the WhatsApp community as well, so you can leisurely refer it. So the architecture of the universe. So in these presentations, just forget about the topics, right? So just grab the content that they have given. So in the universe, we have the solar system. So that is known as a collection of planets orbiting around a common star. And galaxy is a massive structure comprising billions of stars. And the universe uh, is the container, or we can say a system where it holds billions of galaxies, right? So here, in order to identify or to get an easy idea, this diagram can be used. So solar system is the blue colored one, which is the smaller units, right? So that is the unit there, the singular form uh, uh, of the system, right? And combination of those solar systems will be making a galaxy, right? So which means here you will be having few more galaxies as well, a few more solar systems included in a galaxy. And combination of galaxies, that is the this yellow coloring, so that is the universe, right? So try to just remember it, remember the diagram, then you can easily define if they ask this in the exam. And there's a small part that we need to discuss about the gravity. So we all discussed about this thing in your first lessons, right? When we are dealing with the forces and all the stuff. So the gravity W will be equal to mg. So this is a direct relationship, an equation having the direct relationship with F equals ma. So we are applying it towards the uh, towards downside. So the force acting downwards will be the weight or the gravitational force. So it will be equal to m, the mass, and g is the gravitational acceleration on that specific planet or the object, right? So gravitational field strength. So here you can see the unit is given. So no need of remembering the units, just try to get the unit there, right? So it will have the same unit as in acceleration, but in this case, they have given it in another form. So W, the weight is a force, which means it will be measured in newtons, and mass, always remember, it is going to be measured in kilograms here. So therefore, the gravitational acceleration, it will be having, still it will be having the acceleration unit, but they have formed another unit, newtons per kilogram. So here, there's a comparison given. So in Earth, we are experiencing a higher gravitational acceleration force, but when it comes to Moon, there's a low gravitational acceleration value. So which means on Moon, the weight will be different, not the mass, right? Not the mass. So mass will be a constant one, right? Which means if you have 1 kilogram mass here, so the same mass will be on the Moon as well. But if we focus on the weight that is going to be exerted from that mass. So we will be having a different value on Earth, but on Moon, we will be having a different weight value, not the mass. So get the idea and try to build up the relationship, right? So weight can be different from each other, but not the mass. Mass remains a constant value. Then there are some orbital mechanics comparison given here, right? So moons, planets, and satellites and comets. So central orbit. So moons are going to be orbiting around the planets, and planets and other satellites, they will be orbiting around a star or the Earth. And the comet, so definitely comets are orbiting the star. So in our orbital system, so it will be the sun, right? And the orbit shape is given. So this table is pretty much important. So all the points, all the orbital mechanics are like, here it is summarized in this table, right? So you can easily remember the tables actually, right? Without just reading the text and trying to memorize all the paragraphs or something like that. Just you can go through a table and you can easily like you are comparing with another factor, right? Comparing with another property, so you can easily remember it. So the orbit shape for moons, it is slightly elliptical. For planets and satellites, slightly elliptical. But when it comes to comets, it is highly elliptical, which means you cannot draw it as a circular structure, right? A circular path. I think we have discussed about these questions in the paper class as well. So there were several questions where you had to draw the path as well. So remember the table, and the speed is given. For the moons, it is near a constant value, and for planets and satellites, another near constant value. So the constant value can change, right? So when it comes to satellites, you might have remember this thing that there are some satellites called geostat satellites or something like that, right? So which means they will be moving at the same speed where the Earth is rotating, right? So depending on our requirement, the speed can be varied, right? But here for the comet, right? For the comet, the speed will be highly variable, right? Speed will be highly variable. So here you need to remember where it is going to be having the highest speed and where it is going to be having the lowest speed, right? So we discussed about these things in the theory classes as well. So it's your job to remember them, okay? Then the orbital speed. So this is the first equation that we come across in this unit. So you can easily remember it. It is going to be 2 pi r over t. So how did I get this? So we assume that the path is going to be a circular one. So if we are going to start from this position, so this object will be moving around this circular path and will be returning here. So you can see easily that the path is a circle, the circumference of a path, right? Circumference of a circle, right? So here, therefore, the orbital path. So actually, we are using speed equals distance over time taken, distance over time taken. So this is the initial equation that we are going to use. So in this case, the distance is a circular one. So therefore, we are using the circumference of the path. We are using the circumference of the path. And the T, capital T value is the time period. So which means the time taken to complete a full cycle, right? The time taken to complete a full cycle or a circle. So this is the equation that you need to remember. So most of the time, this equation will be given in the equation booklet or that formula sheet, but try to remember it, right? Try to remember it. And there's a small difference when it comes to this R value. So here you can see the R is the radius, but there are some cases where they are giving the radius of Earth as well, right? So if we consider that point, I'll use a different, yeah. So let's imagine, this is the path of the satellite or something like that. So it is moving in this direction, and we have our Earth, and also they have given the Earth radius as well, and also distance from the surface of the Earth to the uh, satellite. So simple R is the distance from the surface of Earth, and capital R is for the radius of Earth, right? So same equation, V equals distance over time, right? Distance over time. So V equals 2, 5. So in this case, the total R value, right? The total length. So it would be the combination of these two, right? It would be the combination of these two. So therefore, Earth radius plus the distance from the surface divided by t, right? So this is the equation that we are going to use in that sort of a situation, right? So remember, first you need to go through the data points that they have given, right? So if it is just a distance, then you can use this equation. But remember, if they have given the Earth radius specially, then you need to go with this equation, right? You need to go with this equation. So try to remember it. Then so it will be having a highly elliptical path, and here you can see if it is away from the star or the sun, so it will be having the slowest speed, and if it is pretty much closer to the sun or the star, it will be having the greatest speed there. It will be having the greatest speed. And then there's an equilibrium of Earth or a star, or like we can say the life cycle of a star is given, right? So there are some definitions given. So how the birth occurs, and the process, and how the star is going to be stable, right? So you can go through these things, and so better to remember that flow chart, how the solar system evolved, or how the star is evolving. So better to remember that flowchart because as I can remember, there are a few questions from that section as well, right? And here, this is the flowchart. So it's better if you can remember the textbook version, or doesn't matter whether you can remember this thing, right? So here there's going to be a protostar, right? Protostar. So that protostar can be divided into where you have an average mass, or there can be a massive mass. So if we consider about the average mass, so this is the normal path. So then the protostar will be evolved to a main sequence star. Then it will be transformed into a red giant star, then a white dwarf, and finally into a black dwarf. So, but if we consider about a massive mass, so the massive mass, it will be converted into a massive main sequence star, then it will be converted to a red supergiant, right? It will be converted to a red supergiant, and afterwards supernova. So that is pretty much unstable, and that supernova will be having two different pathways. So either it can be converted into a neutron star or into a black hole like this, right? So when you are mentioning the flow chart or the what do you call the life cycle of a star, so better to mention this thing. So it's your choice. You can either choose to remember this one or the textbook's flow chart, right? Then the color of heat, right? Better to remember the colors. So if you are having red color, so that is a low temperature. But if you are having a higher temperature, then it will be a blue color. So same thing will be used in that explanation in red shift and blue shift. So red shift means, so if we are having a color here, yellow color, so just imagine this is converted to a red color, then that is known as the red shift, which means the surface temperature has been decreased. But if it is converted here, transformed here, then it will be like, the temperature increase. So therefore, the star will be displaying a blue color thing, right? It will be displaying as a blue colored one. Then measuring the brightness, right? So here, the absolute magnitude. So this is the thing that you need to remember, right? So it will be measured uh, at a certain distance. So as in this diagram, you can see there's an observer on the Earth, and there's a standard distance. So at the standard distance, we will be measuring how much of uh, brightness that is going to be given, right? So go through the definitions, try to remember them, right? And HR diagram. So this is pretty much important. The reason is like there were a few questions where they have given the graph, and they were mentioning red giant is here, super giant is here. Likewise, they were asking you to mention those specific points on the graph. So you need to know what is going to be the main sequence, and where is the supergiants are going to be situated, and the white dwarfs likewise, right? So which means, so pretty much the astrophysics lesson is going to be something like memorizing stuff, right? Something related, something like biology, or like most of the theory points, they are going to be like we need to memorize them, right? As I mentioned in the earlier, we had just two or yeah, we just have two equations in this unit, okay? So go through the HR diagram and cosmology and the Big Bang. So you can refer these things, right? And evidence for the redshift and the Doppler equation. So redshift and the blue shift, as I mentioned. So we know about Doppler equation or the Doppler effect. So Doppler effect means we are observing different frequencies or wavelengths because of the source is being the wave source, right? The wave source is changing its place, or the observer is changed, right? So likewise here you can see if the galaxy is moving away from you, then it will be displayed as a red one. So this is the Doppler equation. So most of the time the Doppler equation will be also given, right? It will be also given in the formula sheet, but better to remember it, right? So here you have delta lambda, which means the difference of the wavelength, right? Difference of the wavelength divided by the reference wavelength. Okay, so Doppler effect proves the galaxies are moving away. The further a galaxy is, the faster it is moving, causing its light wavelength to increase and shift towards the red end of the spectrum, right? So please pay attention to those points. And the second evidence. So this evidence, like the last three slides are mentioning about the Big Bang theory, right? So these are the evidence to prove the Big Bang theory. So in Big Bang theory, what it says is that like there was a huge explosion, and so if there's an explosion, then there must be released energy as well, right? So these are the points. These are the evidence that we can prove that Big Bang theory is acceptable, right? So the first one is the redshift and the Doppler effect. So once a star or a solar system is going away, right, moving away from the Earth because of this energy expansion, then it will be displayed as a red colored uh, star or something like that. And when it comes to the second evidence, so we will be using CMB, or which is known as the cosmic microwave background radiation. So here we can see this is the place where the Big Bang occurs. So here you can see high energy, which means high frequency and low wavelength. But once we observe at the end of the galaxy, so we can see they are having a higher wavelength, which is similar to microwave uh, radiation, right? So here today we observe this leftover heat as cosmic microwave background radiation, CMBR or CMB, uniformly in every direction in the galaxy, uh, which is result in that proving part. Okay, as the physical space of the universe expanded, these waves are stretched, right? So which means they are tend to go forward towards the microwave section, right? So here the astrophysics part is actually easy. As I mentioned, like 80%, 90% of the unit is just theory parts, right? So just you need to go through them and try to remember them. There are only two equations that you need to remember, and those are also easy equations. Just you need to apply the data and you can easily get the answers, right? So that is the end for the astrophysics part, and I will be covering that momentum and turning effect part as well, right? So just give me a few